So last time we started section 1.3, and we're taking a look at evaluating limits algebraically or analytically. And we had ended up talking about these right here, where we noticed that if we tried to plug the number in for x, we end up getting 0 over 0. And we talked about that meaning that there's some kind of factoring that's going to go on. These first two are just real basic factoring techniques that you started learning in Algebra 1, continued in Algebra 2 or college algebra classes, those kinds of things. And we ended up looking at this for just a second and saying, hey, there's radicals involved. I bet something different's going to happen, right? All right. Now, if we try to put 0 in here for x, what will happen? We get another 0 over 0, right? So the 0 over 0 occurring is sort of our red flag for letting us know that there is a way to simplify something that we will be able to do something with. And the ones we've seen so far is it's factoring. This one's not going to look like factoring exactly because of the radicals. So as always, just because there's a radical doesn't mean that you don't just attempt to put in the value, because you still might be able to, depending on what the radical involves. But on this one, you can't. So what I'd like to show you is how you handle radicals where you end up the 0 over 0 going on here. All right, so if I use the phrase rationalizing the denominator, does that sound like a familiar phrase? Yeah. Yes, okay. We're going to do something with rationalizing, but we're not going to be rationalizing the denominator because the radicals are not in the denominator, they're in the numerator, yeah? So we're going to do something called rationalizing the numerator. That makes sense. That's where the radicals are. All right, so taking a look at what we have here, I'm going to move my 0 over 0 over because I want the space to be right there. When we rationalized the denominator, if what's in my numerator had been in the denominator, what we would have done is to multiply by what is in this numerator, but it would have a positive sign between the square roots. Okay? So rationalizing literally means, for the purposes of what we're doing here, getting rid of radicals. That's our goal. So I'd like to talk about why that gets rid of radicals. Now, in the numerator, you have two pieces with subtraction on the original piece you're given. What we've done is we've done the two pieces of radicals with addition between them. But when you multiply a binomial, two pieces, by another binomial, you have to FOIL or distribute. Shake your head if that sounds like things you've talked about before, right? Good. But what happens when we multiply in these two situations is that these two, what happens when these two get multiplied? Yeah, the square root cancels out. Like we're going to simply be left with 2 plus x, right? That's great. And what happens when we do this, hang on. With these two, is they don't cancel out, yes? Okay, these two will not cancel out. However, if you'll notice, it's the same thing I get with the blue ones. So the blue will give me the same thing as the red, except for what?
It'll be a negative.
It'll be a negative. So one's going to be positive and one's going to be negative. So these two are going to give me the same quantity as these two are going to give me, but one's going to be positive and one's going to be negative, which means they're going to add to 0. Okay, so another sort of phrasing of that, sort of cryptic-like, is that when you FOIL, the inner and the outer terms cancel out. Right? So the parts that would still have radicals in them actually add to 0, and so we don't actually end up with any radicals from the inner and the outer terms. Not only that, but, let me get rid of all these colors for the moment now. When I multiply these two together, what will I get? I'll get a 2. Positive or negative? Negative 2. So the last terms will also get rid of the radical. So the first terms get rid of the radical. Oh, the square root went away when I did that. The first two terms eliminated the radical because I multiplied a radical by itself. The last terms eliminated the radical because I multiplied a radical by itself. And then the inner and the outer terms cancel because they are additive inverses of one another. They add to 0. Okay, that always happens when we multiply by what's called the conjugate. So if we have the square root of 2 plus x minus the square root of 2, and the square root of 2 plus x plus the square root of 2, those are called conjugates. Okay? And what's actually happening here, and we saw it happen on problem number 3 here last time, is that it's a difference of squares. Differences of squares don't have that in-between term. If I multiply x plus 3 and x minus 3, those are conjugates. And I don't end up with the inner term, the middle term, that the inner and the outer would add up to being, because they add up to 0. So this is just a glorified version of problem number 3, but it looks quite different. I don't get the radicals, however, to go away everywhere. In some sense, I've sort of just moved the radicals to the bottom. But it's actually okay. We don't have to distribute them or anything like that. We're just going to write them in the parenthesis. What did I have? 2 plus x. After the x. And as we talked about last time, until I'm actually substituting 0 in for x, I'm going to write limit as x approaches 0 on every single step. What do you see happen on top next? Don't overthink it. It's just x. I have a positive 2 and I have a negative 2. I'm going to write one more in-between step. This is kind of an optional step, so I'm going to put it over here on the right-hand side. So if you don't want to write this step out and you just want to jump to the one I'm going to do next, that would be okay. But I want you to see that right now, this is where I am. What would be our next cancellation? Yeah, the x's, right? So since the x on top cancels with the x on bottom, which you could have recognized over here, you might have seen it already and thought, why don't we just do that? That'd be okay if you could have done it there, okay? I end up having a 1 on top. And I have that square root of 2 plus x plus square root of 2 on bottom. Can I put 0 in now? I can. In particular, you know you can because you don't have a 0. You don't have any ability to get 0 on top anymore. There's a 1 on top. It's just a constant. So I'm going to be able to put 0 in for x. So at this point, I can avoid writing limits anymore, and I can put 0 in. Yes, Kingston?
Why couldn't you put 0 in on the second step after you rationalize?
You mean like right here?
Yeah.
Before I canceled the x's, I still would have had 0 as over 0.
Oh.
That's why. I have to cancel those x's. That's what's causing the problem at that point, is that there's a 0 on top with x there and a 0 on the bottom with the x there. That's a good question. Does everybody see that? So until I've simplified enough, and sometimes you can put it in before others, so you don't have to it doesn't have to be the ultimate simplification thing that you might have done in an algebra course. At whatever point you're able to put the 0 in for the x or the 2 in for the x, whatever it is, that's the point when you can do it. I'm just not able to until I get to the step that's at the very bottom of my screen right now. There wasn't the ability to do so. So at this point, I have the 1 on the top. And I'm going to show it out just so that you see it in your notes if you want later. And if you didn't, you just wanted to write that out with the 0, without the 0, that would be fine. I can put the 0 in for the x. This gives me 1 over square root 2 plus square root 2. So what is square root 2 plus square root 2? 2 square root 2. Okay? But this is a number. Agreed? It's a number. It's not a very lovely looking number. It's got a radical in there. And at this point in my final answer, I do want to have a denominator that's in rational form, which means I'm not going to leave a square root 2 on bottom. And the way that I eliminate a simple square root 2, not square root 2 plus x from above kind of stuff, but just the simple square root 2 is that I multiply by the square root of 2. So I'm going to get the square root of 2 on top. But these two, what's the square root of 2 times the square root of 2? 2. And then multiplied by the 2 that's on the outside gives me a 4. And I can't simplify this any further. Do I still have a radical? Of course I do. But it's not in the denominator, so I get to stop. In addition, the 2 and the 4 can't simplify even though they're both even because one's under a radical and one isn't. Okay? So keep in mind that these pieces are different kinds of pieces, hence they can't be simplified, and we would be finished. Now, this is a really good example of one where our numerical approaches and our graphical approaches would come up short. If you traced along this on a graph, it's never going to tell you square root 2 over 4 is your limit. If you put all of this into a table, it's never going to come back and tell you square root of 2 over 4 is your limit, because it doesn't give you an irrational, complete version, right? It gives you a decimal approximation. Now, if you wanted to see if the decimal approximation is close to what we would get for the decimal of square root 2 over 4, you could do that, but you can't turn it back into the radical square root 2 over 4. Analytically or algebraically is the only option here for getting a complete picture of the value, a perfect valued number. Any questions on this? Okay, we're going to shift gears to doing trig, which reminds me also to tell you, some of you are done, and that's wonderful, but not all of you have even been in to see me yet. So come see me for your trig quizzes, right? That's the reason the primary reason I sent out the office hours, is so that you can come in and start taking care of those. The deadline is Friday. Again, if my office hours and your availability are not matching up, let me know, and I'll find somebody else who can give the quiz to you. That's not a problem. There's somebody there almost every point of the day, okay? So let me know if you need it at a different time. All right, so trig. The limits of trig functions work just like everything we've seen before. If I have sine of x, I can evaluate x at c. Cotangent of x, I can evaluate x at c. They're all the same as long as it's in the domain. So there are some places, in particular for tangent, cotangent, secant, and cosecant, where I get asymptotes. Shake your head if you remember that asymptotes occur on a lot of these graphs. Yeah. So there are some values for which I can't put in a value, right? Like I can't do the tangent of pi over 4. Tangent of pi over 4 is undefined. But for every value that is defined or is in the domain, it will work. So once again, with the exception of that 0 over 0 case that we saw in our last 3 examples, limits are really friendly. They're just evaluating the function, right? We just take the value for x, we plug it in, and we get what we get. Worked for rationals, except for the 0 over 0. It worked for radicals. It worked, except for the 0, 0. It worked for polynomials, and that works for trig functions. Okay, so it works the way we would expect it to work. There are some cases where 0 over 0s occur, and they're called special trig limits. So these are our 2 special trigonometric limits. The limit as x approaches 0 of sine of x over x is 1. This is a definition. We're not trying to prove this right now. And the limit as x approaches 0 of 1 minus cosine of x over x is equal to 0. And verifications for this do show up in your book. We talk more about them specifically in Calc 2. But the reason that we need these limits to show up and to have these special trig definitions here is because if you do attempt to put 0 in, we'll just look at sine of x over x. Do you know what the sine of 0 is?
0.
It's 0. So this would give me, if I tried to do it just like I was doing the other ones, it would give me 0 over 0 if I attempted to plug it in, right? It would. And the same thing would happen over here on number 2. The cosine of 0 is actually 1, so 1 minus 1 would be 0. I'd have 0 over 0. So sometimes 0 over 0 gives you a limit value that's 1. That's number 1 here. And sometimes 0 over 0 gives you a limit value that's 0. That's number 2. And you saw over here, right? Here, 0 over 0 gave you a limit value that's square root 2 over 4. And over here, we got 1/2 and negative 1/6. So 0 over 0 does not have any meaning. It means I have to eliminate something to figure out what's really going on behind the scenes. Okay? So for these two, these are definitions that we'll want to just simply remember and I'll show you how to utilize them. We've got a few examples with trig in them. Okay, you ready to get started with the trig ones? Okay, so again, lots of the time, these work out just really friendly. We just put the number in and we're good to go. It's only when we end up seeing that 0 over 0 show up that we have to pause and say, now wait a minute, that didn't work. So if I attempt to put in 2 here, let's see what will happen. I have the sign of pi times 2 over 2. The 2's will reduce, right, to 1. This gives me the sign of pi, and we've been working on trig quizzes. So what is the sign of pi?
0.
It is 0. So this limit is 0. Not 0 over 0 causing problems, just 0. That's okay. I can have an answer of 0. Okay, is that all right? Okay, number 7 is a straightforward one too. I don't even see any denominators to try to cause me problems on this one, right? So this one, oops, I didn't mean to write that, is the cosine of 5 pi over 6. So again, this is why we're doing trig quizzes, is because I want to get you back in the habit of thinking about these values. What is the cosine of 5 pi over 6? Let's work through it as a reminder on this one just so that you can think about it. Which quadrant is 5 pi over 6 in? It is in 2. 5 pi over 6 is the lowest one down here on your unit circle. Wow, that's a fat unit circle. We don't want that. Let's try this again. Okay, so here we are on this point on their unit circle. It has the ordered pairs where you get the square root 3 over 2 and the 1/2, right? Those are the two values you get there. Which one's the x value? Let's go with that. Square root of 3 over 2. And visually, hopefully, as you look at this, you can see why. X, you're further away from the y-axis or the x value, right? This x value right here is a bigger value than this y value, agreed? Okay, so thinking through how we reason through this, this would be the square root 3 over 2, and then I'd have the 1/2. How about signs? Are both of them positive? Do we have positives and negatives? What do we have here? Yeah, the x is negative because we're in quadrant 2, and the y is positive because we're in quadrant 2. Everybody good? Okay, thinking through this, remembering how this works. For those of you who haven't taken one of these quizzes, you actually have a unit circle you can fill in on the quiz. It's not graded, but if it helps you as a reference point, you have it. Okay, so here's our values. Cosine is cosine, or what is cosine in terms of this ordered pair? It's the x value. The cosine is the x value. Sine is the y value, and all 4 of the others are some relationship, right? Either they're the reciprocal, or they're, sine over cosine, x over y, or y over x, those kinds of things. So this one should be what? Negative square root 3 over 2. That's my trig value here. Again, this is one of those things that your calculator is not super helpful in finding for you. It can verify it for you, right? If you're trying to figure out which one it is, this is not for the quiz itself because you can't use calculators on your quiz. But if you're trying to do this in real time in your homework or on a test or a quiz or something like that where you have your calculator at your disposal, it's not ideal. It won't give you back square root 3 over 2 as an answer, ever. If it had been 1/2, you'd be great to go, right? No problem. But it won't give you square root 3 over 2. However, if you know the approximate value of square root 3 over 2 in decimal form, you can probably reason it out, right? If you plug in your calculator square root 3 over 2, what's the decimal approximation it gives you? Somebody tell me what you get. I think it's 0.8 something. 0.866 something, right? So if you were to put in your calculator right now, cosine 5 pi over 6. Make sure you're in radians. I haven't told you that yet, but your mode needs to be in radians for the whole semester. So if you've flipped back and forth when you're in a trig class or whatever, go ahead and put it in radians. If it tells you cosine 5 pi over 6 and you tell your calculator and you plug it in, it's going to give you negative 0.866 something, whatever. And if you recognize, hey, that's the same thing as square root 3 over 2, you can use your calculator to be helpful. You just can't use your calculator to turn it into the radical 3 over 2 notation. Does that make sense? Okay, so any questions on number 7? Either from the perspective of the calculator or the unit circle, any of that? Okay, so let's try a couple others then. Number 8 says the limit as x approaches 0 of sine of x over 5x. What will happen if you put in x is equal to 0 here? You get 0 over 0. So just like with the algebra ones, when we have 0 over 0, we have to stop and ask ourselves what to do. The difference is that when we did it with algebra, the answer was we factored. Or maybe we had to multiply the conjugate if we were doing radicals, right? Here, that's not what we're doing. When we get 0 over 0, we're back to looking at these special trig limits. And which of these two is this one going to look most like? The first one. It looks like sine x over x. There's just this extra 5 going on here, right? So here's how we handle that. We need to take this 5 out in front. But it isn't really 5 I'm pulling in front. The 5's in the denominator, so what am I really pulling out in front? 1/5. So I need to write this step. 1/5, the limit as x approaches 0, of sine of x over x. Is that all right? At this point, this piece looks exactly like special trig limit number 1, doesn't it? So this piece is now equal to 1, and it simply gets replaced by 1. So it becomes 1/5 times 1, and my answer would be 1/5. Is that okay? Let's take a look at number 9. So number 9, clearly, if I put 0 in the denominator, I get 0. What if I put 0 in the numerator? What is cosine of 0 times tangent of 0? Maybe let's just actually do all the pieces as a reminder, because that's good review. What is the cosine of 0?
1.
It is 1. What is the tangent of 0?
Root 3.
Nope.
Root 3 over 3.
It is defined. It's not root 3 over 3.
It's 0.
It's 0. Yeah. The tangent of 0 is actually 0. So we have 1 times 0 over 0. So we really do have 0 over 0, right? But this doesn't really look like either of these special trig limits, correct? It's got a cosine in it, but it's not 1 minus cosine. The first one, it doesn't look like that because there's two pieces. There's a cosine and a tangent. So what's going on there? Well, what's going on there is what we are doing in your other quiz that you're taking in my office. There are fundamental identities that allow you to combine cosine of x times tangent of x. In particular, you can rewrite like this. Cosine of x is good, just like it is. But the tangent is the same thing as sine of x over x. I'm sorry, sine of x over cosine of x. Right? When in doubt, probably, whether you had Dr. Tucker or Dr. Marsh for trig, or if you took trig somewhere else, somebody said, turn them all into sines and cosines and see what cancels out. That's a pretty good default, right? If you don't know what else you necessarily should do, it's a decent place to start. And here, it's actually quite helpful, because what's going to happen?
Cosine.
You bet. Cosines are going to cancel out. We're going to end up with the limit as x approaches 0 of sine of x over x. And that's one of our special trig limits. The same one that we saw before. This is equal to 1. Notice again, limit is on every step. Notice in my blue box at the front, I can't replace it with 1 until it looks exactly like one of the trig limits. So that 1/5 has to be pulled out before you actually do a replacement. Any questions or concerns about these? Okay.